event and for having me here. It's nice to be home. Yes. So the work I'm going to talk about, well, first of all, is not really related to model theory, but model theory has had inputs in various aspects of problems related to the ones I'm going to talk about. So I'm hoping maybe someone can find some connections. And second, it has this long title, Towards Quantitative Versions of the Dynamical Bogomolov Conjecture. That's a mouthful. We are going to take some time to explain the words, because I'm not assuming everybody is familiar here with the dynamical Bogomolov conjecture. But for now, yes, the key word is towards. Okay. And before I begin, all the theorems I'm going to mention are joint work in progress or preparation with Jit Hu Yap, who is a grad student finishing or soon or finished recently. He's defended. Okay. So, also, if I write something on the board and you cannot read or you can't hear me, feel free to interrupt me at any moment. Yes, to get that out of the way. Right. So I'll start with an easier problem, the so-called the dynamical Manning-Mumford conjecture. And this was originally proposed by Zhang in 2006, and later reformulated by Zhang, Gyoka, and Tucker, and more recently re-reformulated by Gyoka and Tucker. And I'm going to state their version. Okay? The last version. So the question here is essentially to understand which subvarieties contain many points that are pre-periodic under an endomorphism. Okay? So to begin, maybe I'll use a little bit of this board. So you have some phi endomorphism of a projective variety over a field which will take to be algebraically closed and of characteristic 0. Okay, and we'll assume that this is polarizable, okay, in the sense that it has some ample line bundle, so that if we pull it back, we get an integral power of itself. Okay. And we'll also fix X as a subvariety, irreducible subvariety. Now, as I said, right, the question is, when does X contain many pre-periodic points for phi? Many means here as a risky dense set. So as a risky closure, the bar denotes the risky closure of X intersection pre-periodic points is X. And then the conjecture wants to say that X having this many, special points that respect iteration should mean that it itself should respect iteration, or that it is pre-periodic under phi itself. Yes. So here, yeah. For a point, pre-periodic is we iterate. To be sure, everybody. Yes. We iterate it, and it returns to previous state. For a point. Yes. Yes. And for a variety, it means the same, but as a set. You iterate it as a set, and it returns as a set. Thank you. Yes. Any questions, please? I know people here have various different backgrounds, and feel free to ask even any kind of questions. Yes, I wrote the statement, it's wrong. This was the original prediction. It turns out there are some pesky counterexamples to this formulation, coming actually from abelian varieties that were discovered by Gioca and Tucker. And so I have to say, or pre-periodic essentially for a commuting endomorphism. Okay. The true statement is a bit more complicated, but I will ignore it. Or pre-periodic or commuting with an iterate. Every time I think I write the right statement and then I read it again and no. Okay, quotes. So I'll call both of these special. But for most cases, you should think just pre-periodic. Okay. Maybe some examples to remind you where it all started and where it's going. Examples. The name of it has the word Mumford conjecture. This story started in a paper of Lang back in 1983, where he discussed some questions that were proposed to him independently by both Manning and Mumford, and that arose in their investigations. And in his example, he was just looking at subvarieties of a power of the multiplicative group. Okay, or and it was asking when do they contain a dense set of points with all coordinates roots of unity. Okay, in our dynamical formulation, we are looking now at subvarieties X in this example of a power, say, of P1, the projective line, and we're looking at the endomorphism of this power of the projective line given by, well, squaring all coordinates. Okay, it's extending the squaring map. So forgetting about the point at infinity, the various points at infinity, here the pre-periodic points are essentially equal to the points with coordinates roots of unity. And so this, I'll write Lang here. Sorry? Prep phi here. Yeah, mu infinity. Okay, roots of unity. Mu infinity is a symbol, denotes the set of roots of unity. Yes. Times itself. Cartesian product. No, it's good, it's good. Thanks, thank you for asking. No. Again, continue to ask. Okay, right, and the conclusion, right, the special things here are just the torsion translates of algebraic subgroups. In Lang's vocabulary, which do happen to be the pre-periodic subvarieties for the square map. Yeah. And that was the first example, and Lang also included a question about what happens for other groups in his paper. For example, for abelian varieties, which is a second example. When do subvarieties of abelian varieties contain a Zariski dense set of torsion points? This is the Manning-Mumford conjecture, the classical one, as I may refer to it later on. In our vocabulary, I want to pick an endomorphism. So we have A here is an abelian variety. And you can just choose the map phi to be the duplication map. And now, I don't know, the little Fermat theorem, I guess, tells you that the pre-periodic points of this map are the torsion points of the abelian variety. So the conjecture, which is here a theorem, says that X contains a Zariski dense set of torsion points, implies, well, that X is, now I need to use actually also the second conclusion, so special for the duplication map, which in group vocabulary means that X is again a torsion translate of an algebraic subgroup, of an abelian subvariety. It has a group structure itself, up to a translate. Okay. This was proven by Reynaud first in '83, and we have many proofs after that. A few of them also using model theory. I believe Laura listed all the authors of all the possible proofs. Pila, Zanier, Hursovsky, possibly others. Don't forget. Okay. Any questions about this? So this was the motivation for the dynamical version. And well, maybe a dynamical example. Well, one appeared in Laura's talk, where she was considering common pre-periodic points of rational maps. Okay, in my vocabulary, this vocabulary, you are looking at a map given by the action of two different degree D rational maps on the affine line. Okay, so this maps X comma Y to Fx y for two degree D rational maps. And well, you can. The question was, when do these two maps have infinitely many common pre-periodic points, or when does a diagonal contain a Zariski dense set of pre-periodic points for this split, so-called. Okay. And in this case, we know that this implies that the diagonal is starting from works of Mimar, and later on, many people, this example, Huan, Zhang, Baker, DeMarco, Yoka, Wen, Yi, yeah, it's a special case of this dynamical question that is known, okay? Kind of the first case that was studied. And then I'll essentially list every case that is known because there are not many. So a generalization of this case to all endomorphisms of powers of the projective line. Okay. Okay. I'll say DMM for dynamical Manning-Mumford is known for these endomorphisms by work of Gyokan, Nguyen, Yi. First for the n equals 2, and then more generally, except then you also need to use some work of mine with Smith of Wilms, Smith and Wilms. Okay. So we say this is a case of split maps that's completely understood. And much more recently, very recently that is, we also obtained a new case for regular polynomial endomorphisms of P2. Okay. Now these ones will come up again later. So I will define what they mean. So these are extensions of polynomial affine endomorphisms from A2 to A2, the affine line. So this means just maps given by two polynomials into variables that extend to P2, and we'll assume then that this polynomial P can be written as, here is the homogeneous degree D part plus lower order terms. And same for Q. Okay. So now you can take this affine map and extend it on P2 by, at infinity, the action is given exactly by these leading terms, the PD and QD. So I will use this notation also later. So P restricted to, this is the line at infinity in P2, will be just PD, QD. So these maps, they have this particular way of acting at infinity. It's very useful to understand their dynamics. And okay, and for certain curves, for curves, okay, I'll say for curves, C in A2 with some technical assumption. This is work of Dujardin, Favre, and Ruggiero. Okay. So, in summary, these are the only cases that are known. Okay. What do I want to talk about here? Motivating question, let's say. Yeah. Yeah, sorry. Yes, I thought you meant I missed some work, but no. If I miss, sorry. The motivating question is, well, assume that X is not special, okay? If X is not special, so then I know that it doesn't contain a dense set of preperiodic points. Well, what can I say? Very vaguely, I'll put this question now. What can I say? Can we say about the degree of a subvariety, which is in X, containing all the preperiodic points that are in X? Okay, it's a very vague question. It will remain vague. For example, right? What is the degree here, right? The degree of a variety for me now will be the sum of the degree of its components, even if they have different dimensions, with respect to your favorite line boundary. It doesn't matter. And well, again, maybe the easiest example to think about is the case of a curve, right? To these two conclusions. So yeah, so that I can assume that this is not an equality. Okay, because if it's inequality, there is nothing more to say. Okay, right. For example, what am I asking? Right, take a curve that's not pre-periodic. How many pre-periodic points does it contain? What can I say about the number of pre-periodic points in a curve? Well, say I cannot compute it. Maybe it can be bounded uniformly in terms of the degree of the curve and the degree of the map. Something like that we saw already in Laura's talk in some example. Maybe I can even write down exactly a concrete bound on how many pre-periodic points it has in terms of the degree of the map and the degree of the curve. Though, okay, that's probably harder, right? For now, this is a vague question. And in order to be able to make it more precise, I kind of need to talk about a more difficult problem, which is in the title, this dynamical Bogomolov conjecture.
So is the Y that you're writing there, are you thinking about that as just like this risky closure of X-intersect pre-periodic, or is it something else?
So maybe it may not exactly be the Zariski closure, but the Zariski closure will be inside it. Yeah. Then you can go down inductively if you can at times. Yes. Yeah, we'll make this a precise statement. But the induction is not always working, so you have to be careful how, yeah. Yes, 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 you can take that to mean, yeah. It could either, yeah. In my mind, they're equivalent, but you are perfectly, in my mind, they're equivalent. But yes, yes. But yeah, you're right. It's also just a vague question, and it's better probably to take it axiomatically, like you put it. Define special to mean, yes. Thank you. Better way to think about it.
Can you finish that sentence? It's better to think axiomatically. Define special to mean.
Yes, thank you. Yeah. So, okay. Take special, phi special to mean X intersect rev phi. Zariski closure is X.
I was just about to ask about your first definition of special being either pre-periodic or pre-periodic. Are there geometric conditions that you could, for example, where it's known that that second thing cannot happen? Right, like if you took a regular polynomial endomorphism, is it possible for it to be?
Yes, no, in this case, okay. Hi, thank you. Good question. In the case, okay, including this assumption on the curve, then from their theorem, it transpires that that second condition cannot happen. Without the assumption, I don't know if it's known. I don't suspect it can happen. Like, it's very hard, at least in P2. But if you go to P3 or P4, maybe it can happen again because you can find the split map counterexamples appearing in PNs as well secretly. Yeah. So it's another different, also interesting question to understand that. Yes. Okay. Right. Upgrading the problem. It's been already, wow. Let's go by. Yes, I'll say in words. Right. I talked about polarizable endomorphisms and so on. From now on, I will just focus on endomorphisms of Pn given by degree D homogeneous polynomials. Okay? Because I'm not losing anything. It's an observation of Fakrudin that everything reduces to that case, thanks to the polarization. Okay, so from now on, P from Pn to Pn. And D denotes the degree of homogeneous polynomials that are used to define it. Okay. For the Bogomolov conjecture. So in particular, okay, the Bogomolov conjecture, right, came after the Manning-Mumford conjecture, and some of the model theory tools now became moot. They couldn't say anything about it, but works of Suhut Zhang and others developed techniques that allowed to treat this more general version that are relevant to us also for today. Okay, I'm being super vague. To start being more precise, having an endomorphism of Pn like this, and now take it to be defined over a number field. We also have a notion of canonical height associated to it, given to us by Colin Silverman, which is a function of the algebraic points to the non-negative real numbers, and it maps a point in Pn to the limit of the height of the iterates of the point divided by d to the n. Here, h is just the veil height, the standard veil height on Pn. Okay, so this turns out to exist and gives you definitely a non-negative real number. And now we also know it's called the canonical height associated to phi. It satisfies this property that if you apply it to the iterate of the point, you get d times the canonical height of the point. And it also has a very important second property that it differs from the veil height by a bounded error term. Okay. From these two, and at least in the case of number fields, because the veil height has an North-Code property, you can also infer that this canonical height vanishes exactly at the pre-periodic points of phi. So when later on I'll take points of canonical height that tend to 0, those are to be thought of as a generalization of the pre-periodic points. Okay. Now, I'll also mention later function fields, okay, by which I'll mean just function fields of a curve, for regular projective curve. And for simplicity, let's just say Q bar B, or B curve. Okay, let's keep it simple. And when we talk about those, well, you can still define this notion as long as you fix this ground field, because you can talk about the veil height on the function field. It measures the degree of the point, essentially. First, you can do it on K, right? And then you can actually extend it to K bar as well. Yes. But this time you need to remember the K you started from. It's kind of what's different from the number fields. Okay. So, but you can do this. You can define a height, and it gives you a non-negative real number. It also satisfies these two properties, though it fails to satisfy this third property because the geometric height does not have the North-Code property. And well, here also, well, we know actually in this case, right? Okay. Let's say star fails, need to consider isotriviality. Just, I wanted to put it here as a warning, like it could be, for example, that the map is defined over Q bar itself, in which case all the Q bar points will have height 0, and it doesn't matter if they're pre-periodic. It turns out this isotriviality phenomena is the only thing we need to consider also, besides the pre-periodic case, that has been actually to characterize the zeros of the canonical height. That is in work of Gautier and Vigny, generalizing work of DeMarco and of Baker. And I will not use this later on, but I wanted to mention it because there is also another approach to this problem by Hatzidakis and Hrusovsky, which I don't understand at all, and maybe someday somebody will explain to me if I mention it enough. In this series of 2 papers that actually Laura had in her slides. Okay. No, don't leave. Okay, so we have this height, perfect. What did I want now? Right, the Bogomolov, now I can state the Bogomolov conjecture, almost, right. The dynamical Bogomolov conjecture. Yes?
What are you saying that this work at the end there does?
So the claim is that it tells me when this canonical height is 0, at least under some assumption that phi has no isotrivial part, in some sense that they define. Yes.
This paper is about percentage difference graph.
Yes, but yes, I think so. That's the title. My knowledge of it is, yeah. In fact, I don't even know, okay, because the result is formulated in a general vocabulary, and in our world, somehow only a corollary of it has become famous. I don't know if it even says more than I think it does, translated in the dynamical context, because I don't understand the most general formulation of the theorem in the paper, which is the general vocabulary of different varieties. Yes. Okay, one more definition, I guess, that will appear later. This, now if I have X as a variety of Pn, just before, I'll define the first phi essential minimum of X to be the essential minimum of the canonical height on X. Essential meaning, well, outside of codimension 1 things. So it's the, I didn't define it, so Zhang defined it, but yeah, it's the supremum over all Y with codimension 1 of the infimum of all the X outside of Y of the canonical height of phi. Okay. When does this become 0, right? This becomes 0 if in X I can find sort of a generic sequence of points with canonical height tending to 0. Okay? So, in particular, if it contains a certain set of pre-periodic points. Okay? Well, the dynamical Bogomolov conjecture, also proposed by Zhang in the same paper, says that, yeah, this essential minimum will also vanish exactly when this X is phi special. And you can take phi special to mean either of the axiomatic definition or the concrete description. It's still just a conjecture. Okay. It is known in all the examples I stated before. Just that in the classical setting, there were new tools to solve it. But in the dynamical setting, the proofs that we have solving the Manning-Mumford version also solve the Bogomolov version. We don't have tools that only do the Manning-Mumford part for every example or so. Okay. So a tool that actually proved very useful, developed, yes, question? Yeah. Developed first for the case of actually, just this case of Lang's theorem, when you ask the Bogomolov version of this problem. So Zhang considered that question, and already then, he developed what is called the fundamental, Zhang's fundamental inequality. Okay, we are getting closer to be able to formulating the theorem. Okay. Now, this inequality does not solve the dynamical Bogomolov conjecture, but it allows us to reduce it to a computation question involving computing the canonical height of now a subvariety. Okay, so Zhang took some kind of intersection theory, Rakelov intersection theory, also developed by Gile and Soule, and he took it to the limit in the sense of some adelic metrized line bundles he defined with a limiting procedure, similar to the Néron and Tate limiting procedure. Okay, for our talk, I'll define the heights of the subvariety in a more concrete way, slightly more, building on work by Philippon and then later David Philippon, which are the names actually very important for our result, for our statement, for our proof, and everything. So here's how I'll define the height of a subvariety. First, just you have any subvariety, it's, let's say, veil height, okay? It's not what Zhang defined, but it's something. Will be just, again, the height of the Zhou form of y divided by the degree of y. Now, the Zhou form of y is just a homogeneous polynomial. And by height, I mean the height of the vector given by the coefficients of that polynomial. Okay? If you haven't seen how to compute the Zhou form, just think of the case of hypersurfaces given by one equation, literally the height of the coefficients of that equation. Okay? So that's a thing. And then we'll iterate this. And the phi canonical height, I'll say, of y will be the limit, as n goes to infinity, of the height of the nth iterate of y over d to the n. Okay. So this was considered, well, let's say this I will attribute to Philippon. This limiting procedure sort of appears in works of David and Philippon dating before 1999, but they didn't consider dynamical systems. For dynamical systems, it was restudied by Hoots. Okay, my canonical height is different than his, in that it's his over the degree of y. Okay, because this way. Now I'll get the nice properties that I had over here. I'll get the nice properties, which are not hard to prove. The iterate of the height of a variety is itself. And actually, by work of Cole Silverman and ideas of Gile Soule, it's also possible to prove the second property. Okay, so this also turns out to be the same as the height Zhang considers for the invariant metric. But let's ignore that. So what's a fundamental inequality theorem, which I'll attribute to Zhang and then to Gubler in the case of function fields. They proved that the first essential minimum is at least 1 over the dimension of x plus 1 times the canonical height of x. In other words, if this canonical height is strictly positive, then I cannot have a dense set of small points. Okay, maybe in other words, to make the same statement again. Okay, I can process it. what's the usual? Yeah, you can use any Hermitian metric.
Oh, so but you can also just do it by iterating.
Yes. That is the same. It's not hard to see if you accept that it satisfies these two properties. Okay. If you accept that both of them satisfy these two properties.
So
Those two properties determine it uniquely.
That means it'll not work out some of the stuff about doing
Hoots actually works it out. Hoots, in this dynamical case, they didn't do dynamics. So. To bound, yeah, periods. Yes. What else? Yeah, and Patrick Ingram also considered it. We'll mention later, hopefully. Yeah, let's rethink that theorem then, the fundamental inequality, because this later formulation will be, will allow me to make my question in the beginning more precise. Okay, it's really weird. So it's the same statement. If delta, I'll say, is strictly smaller than 1 over dimension of x plus 1, then the set, say, A of delta, given by all the points in xk bar with canonical height at most delta times the height of x, okay, is not Zariski dense in x. So take a moment. It's a contrapositive of the same theorem. It's the same statement, okay? To think about it again, right? Well, it tells me that this constant, the canonical height of x, kind of determines a height gap for most points in x. There's something delicate that I cheat a little bit always. I made this inequality strict and everything strict. Well, if it happens that this guy is 0, right? When we expect the Zariski dense set of torsion points or everything, well, this strict inequality gives me that this A delta is empty. So it's a vacuum statement, but makes sense. Okay? Right. So we have the set, there's a gap. And now my question, to be more precise, is, right, can we quantify this non-Zariski density? Okay. What more can we say about a subvariety containing this set? Maybe at the expense of shrinking this delta. And that's what we'll do. We'll write down the main theorem, which will be long. Okay, I have 6 minutes. And we'll give a precise bound. Okay, theorem. Yep. In progress. And jump down to it. Right. So we'll take K to be the number field or the function field we had before. And we'll fix some N for Pn and some D for this polarization degree. Okay. Then there are explicit constants. C1 that depend on N and D, and C2 that also depends on N and D. I'll say more about them. Such that if C is a degree D endomorphism of Pn, X is a subvariety of Pn, also over Q bar, both of them. Then the set of points in K bar with canonical height. And now I'll have some number exponential in the dimension of X in the denominator. So 1 over, you can ignore the precise numbers because chances are they will change by the time this is posted. Okay. So this anti-height gap set is contained in a subvariety of degree at most. Okay, and now the monster. Well, I'll put some numbers here symbolically. 8, 4e, something again exponential in the dimension of X, and then C1 times the height of phi, by which I mean the height of the vector given by the coefficients of phi, plus C2 over the canonical height of X plus 1 to the, I don't know, I'll put 12 dimension X today, times 2 to the, let's put 8n, times e to the 2 dmax, times something now polynomial in the dimension. Let's put this to the, okay. The precise numbers are immaterial. This is a form of the expression. The expression is in terms of the dimension of X, this capital N and D, the degree of the map, and here we see also the height of phi and the canonical height of X. Okay, we'll process it slowly. What this all mean? Not so slowly because, okay, within 5 minutes. First of all, yeah, maybe the first thing I'll say is the last thing I would have said if I had time. These C1s and C2 these C1s and C2 come from a difference between the canonical height and the veil height. So it's been proven by Ingram and is getting generalized in the thesis of his student, David Martinez, that this canonical height over minus the veil height is at most C1 height of phi plus C2. Okay, C1 looks like, will look like n d to the n plus 1, and C2 is worse. Ignore the numbers. The nature of the things matter. Okay. Now looking at the statement again to process what it says. Forget about the general case, just curves. Okay, so count number of points. This set contains all the points in X that are phi periodic. Right? Maybe let's just go just back to the example of Laura's talk, where we had just two maps, F and G. Right? What does this say? It says that if we knew, if we could find epsilon such that the canonical height of the diagonal is at least epsilon times maximum 1 height of Fg, then the number of common pre-periodic points of F and G would be bounded above by a constant that you can compute explicitly in terms of the degree of F and G and this epsilon. right? Okay, and this was actually the strategy the Markov, Krieger, and he followed to get uniformity in this example, right? Except to prove this reduction, well, they used ideas from the work of Favre and Rivera-Letellier and Philly, using quantitative equidistribution and in potential theoretic terms and bounding Helder exponents explicitly in terms of the dynamics of the maps. And so it worked to give you this result. In fact, it gave you a better function of epsilon than this that we're getting here. So it saved you, I don't know, it saved you maybe this 12th exponent. Right? But it's, and it has been generalized to maps of degree D like this by Yap and Senk, and by Gautier more recently. But it's hard to generalize this method to arbitrary curves even here, or in higher dimensions. I mean, at least Zitwu had tried a lot, and Gautier also. Yeah, so this the proof of our theorem is totally different. It's in fact already kind of there in the work of David and Philippon. So if I say maybe one word before I stop, right? To prove it, the observation is that because of this control in the difference between the height and the canonical height, and because of this property of the canonical height that it grows with iteration, right? All you have to do is prove an analogous statement for the veil height. Okay, and that would be difficult, except David and Philippon, at least for number fields, had already done it. And to do it, okay, they used a lot of things, and we had to generalize them for function fields. So for function fields, we rely on an absolute Siegel theorem by Roy and Thunder, which uses geometry of numbers, and then that proves that there exists kind of a small section in some sense, but then we have to compare this notion of smallness with what we actually need, and there, David and Philippon's ideas were actually from commutative algebra more and elimination theory, and is what we use. So I will stop here.
Questions?
Yes.
How exciting. Okay. So